Hello and welcome to Wagner Academy. This is Geometry Lesson 1.6. We are talking about polygons in this lesson. Lots of terminology in this one. However, you probably know, I would say, at least half of these by now, and some of them you might just need a little refresher on what they mean, but a lot of them are just different names for types of shapes. And make sure if you're one of my students, hey, you know what? There's extra examples in your book. Use those along with these ones to help you do your assignments. Let's get started. Geometry 1.6 polygons. We have this first blank is the name of the lesson, polygon. So a polygon is a closed figure whose sides are all segments. That's the basic idea. So everything's closed and the sides are all segments. The book has a more technical definition than I'm going to get into here. I'm going to show you examples and describe the more technical definition, but I won't actually write it down. If you want to write down more of the technical things, check out your book or write down the things that I say out loud. So first of all, some examples of polygons. These are going to be closed figures whose side lengths or whose sides are all segments. So I could have one there, there, and there. Your triangle, if you're doing this on your notes, it doesn't have to look exactly like mine. So I'm saying this is closed. This is all connecting right at the endpoint. So this is connecting here, here, and here right at the endpoints of those segments. That is one example of a polygon. You might know what kind of polygon that is, but I'm not going to say that quite yet. Here's another example of a polygon. So something like that would still be a polygon, even though it kind of caves in like that. Still a polygon there. And just so if you're really picky, that's closed right there. Okay, so there's a tiny little opening. I don't want you to think that that should be there. And so a final example of a polygon. There shouldn't be any overlapping sides like that either. So I just want to make this as precise looking as I can. Okay, so that would be an example of a polygon. And again, yours don't have to look exactly like mine, as long as they are closed figures like this with no overlapping parts and no intersecting parts where one carries over the other side. No curved parts either. We're going to talk about examples of polygons. I think it's actually more helpful to know what a polygon is by looking at things that aren't polygons. So these things are not polygons that I'm drawing here. So far so good. It's got all segments and they're all connecting, but then I'm going to leave it open right there. So you have this opening. That means it's not a polygon. You could also have something like this. This would not be a polygon either. So notice how the segments cross over each other like that. And again, I'm not being real technical with some of the ways I'm saying these things. I want you to get the idea more than to have some technical definition written down. If you want to see the more technical definition, check out your book. And then something like this would also not be a polygon. It's all closed up, but it's got curved parts to it. So what are the big things that make these not polygons? For this one, you had an opening in the polygon, so no openings. For this one, you had curved parts. There's no curves allowed. And for this one, for lack of a better way to say this, no crossing segments. So these segments cross each other. That's no good either. And then don't draw what I'm about to draw here. Just listen to this part. But if you had something like this is what I was trying to get at earlier. You had a segment that went to the endpoint, but then it carried over a little bit farther than that. That would not be a polygon because you don't have the endpoints meeting up where they're supposed to be. They're supposed to meet up right at their endpoints with all the segments. So some examples now of down here, something called convex polygons. And then over here we'll have concave polygons. I talked about some polygons caving in. That was kind of a hint or leading us into this example. So here's some convex polygons, some examples of convex polygons. I don't want you to think there's an open side there. There we go. This one looks like a trapezoid to me. And I'm going to draw a triangle in here. A little more precise there. Make sure those are closed. And I'll move that in just a little bit. There we go. And I suppose if I'm going to get real picky, I want to be precise with these drawings. So I'm going to bring this in just a touch. Just a hair. There we go. And let's do a hexagon for this last one. So hexagon, what's that mean? That means 6 sides. We're getting to that. We haven't talked about that yet, but that's coming in this lesson. So there we go. Those are all convex polygons. I think, again, it's easier to show you what concave polygons are to help you understand better what convex polygons are, just as it was up here to show you non-examples to help you understand what a polygon was. So concave examples would be something like this. We've got one of the parts kind of caving in like that. So that's one example of a concave polygon. Here's another example. Here we have 2 parts caving in. As long as you have one part, that's all you need. Oops. And again, I don't want you... Oh, what is going on? Do I have the right thing selected? No. Okay. Grab it. There we go. Close it up. All right, and a final example for here. Kind of looks like a square Pac-Man to me. There we go. So what makes these concave? What makes these convex? If you have a different color, this would be a great time to use that. If you don't, I would say do this with hidden lines instead. I'm just going to show you on one of these pictures in each one here, and then you could do the rest if you wanted to. So I'm going to go with red. So let's assume that that continued up this way and down this way, that all these segments continued on forever, whoops, in these directions here. So I'm not drawing perfectly straight lines, but I hope you get the idea here what I'm trying to do. There we go. And then over here, do something similar here and here. So what makes these concave, other than the fact that, yeah, they cave in, but being a little more technical, a little more precise with our language, the way we're describing these things. Notice how these lines, if we extend these segments through all the way this way and this way, make lines out of those. This one, you have lines that actually cut through the polygon. And so because of that, because it cuts through the polygon, it's not convex. These ones, no matter what segment you extend out, none of those lines cut through the polygon. That means it's convex. So that's a more technical way to describe that. Here they cut through the polygon. I could draw in this segment and this segment farther, but I think that's enough to show you that those lines extended cut through the polygon. Moving on now to some names of polygons. So you probably know a lot of these. That was going back to the terminology. That was from here to here. But pretend you didn't see that. Let's see if we can fill this out without looking back at that. So number of sides. These are the ones you need to memorize. You need to have down by heart. So 5, 6, 7, 8 sides, 9 sides, 10 sides, and then we skip 11 and go to 12, and then just any general number n. What would you call that? So for 3 sides, that's a triangle. 4 sides, the general name for a 4-sided shape is a quadrilateral. We have more specific types of quadrilaterals like squares, rectangles, rhombuses, trapezoids, parallelograms, etc. But quadrilateral is the general name. For a 5-sided shape, it's a pentagon. 6 sides, that's a hexagon. 7 sides, a heptagon. 8, like an octopus, is an octagon. I almost wrote octopus. 7 I remember because of the heptathlon. I'm a big track and field Olympics guy. The heptathlon is the 7 event track and field event that they do over the course of a couple days that the women do. 9 is a nonagon. 9 and non kind of sound alike. That's how I remember those two. A decade has 10 years. A decagon has 10 sides. A decathlon has 10 events. So that's how I keep those straight. And then a dodecagon. It's kind of like a decagon with 2 extra letters. So 12. 2 plus 10. And then this one is an n-gon. I literally just thought of that. I've never thought about it that way. But if that helps you, great. I forgot to mention what these pictures are doing over here in this slide. So notice how this face is actually composed of polygons. So polygons, there's a very good real-life application here, talking about video games, talking about movies that use computer animation. Polygons are used all the time with animation. So if that's something you're interested in, knowing how polygons work and how you can arrange them and different properties and whatnot about polygons, I think that'd be pretty important to know if that's a career field you're interested in. So a regular polygon, for this next bullet point here, a regular polygon is a convex, so it's got to be convex, no caving in parts. Convex polygon in which all of the sides, and I'm going to double underline that, and angles, so both have to be true. Sides and angles are congruent. Over here are some examples of regular polygons. This would be a regular triangle, a regular quadrilateral, which we call a square. This one we call an equilateral triangle. Then you have a regular pentagon, hexagon, heptagon, octagon. So example 1, let's put this information into practice. Name each polygon below by its number of sides. Then classify it as convex or concave, and regular or irregular. So before I have any markings on this picture, you might look at that and say, well, that's looks like at least a irregular convex hexagon. And I would say yes, it does in fact look like that, but could you say that for sure unless you're given information about it? No. So let's draw some information on this picture. I'm going to tell you that this stuff is true in the picture. So draw tick marks, the same number of tick marks on each segment, and draw the same number of arc marks in each angle. After doing that, now can you say this is a regular convex hexagon? Absolutely. We could have said it was convex. We could have said it was a hexagon, but we couldn't say for sure that it was regular until we had that extra information in the picture. So this is a hexagon because it has 6 sides. This is convex. You have no caving in parts. And it is regular because all the sides and all the angles are the same. And it was convex to begin with. So you have to start with a convex shape to begin with, and then the sides and angles are congruent to be regular. On this one, we're going to add some extra information as well into the picture. So I want you to put 1 tick mark on all the segments in this picture. And all these angles here that I'm marking, put 1 arc mark in each one of those angles. So after doing that, let's count how many sides we have. So with a shape like this, when you have a shape that has more sides than is easily counted by just a quick glance, it's, I think, a good idea to make a little point on the picture and then go around the shape until you get back to that point. So let's start here. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sides. We got back to our point. So a 10-sided shape, this star is actually a decagon. And is it convex or concave? Well, we have these caving in parts all over the place. This is definitely concave. Because it is concave, it cannot be regular. Regular polygon, by definition, is convex. So even though we have all equal sides, we call that equilateral. This is an equilateral shape. These 5 angles are the same, but these interior angles are actually kind of, in a sense, bigger than 180. So this one, this one, this one, these angles are not the same as those. This is irregular for that reason, and because it was concave. So if something's not regular, it's irregular. Those are your only 2 choices. Now, looking at our third slide, we have the perimeter. That's what we're going to talk about for the remainder of this lesson, the perimeter of polygons. So the perimeter of a polygon is the sum, in other words, SUM, we're adding the lengths of its sides. So in example 2, find the perimeter of a rectangular plot of land that has a length of 516 feet and a width of 380 feet. Let's label our picture as such. So we have 80 feet. And then down here our length is 516 feet. And if we find the perimeter of that, we use capital P to represent perimeter, and we simply add the sides as the sum of the lengths of the sides. So if I say this is my length, I'll use a cursive L for that. Use a cursive L instead of a regular print L so it doesn't look like a 1, and then a W for width. I know that I have my length here and my width here as well. So I have a length plus a width plus another length plus another width. So you've probably seen this shortcut formula before sometime, or if not, it's pretty easy to figure out where that comes from. If you want to use this for rectangles as a shortcut formula, feel totally free to do that. So this is a shortcut formula for the perimeter of rectangles. Okay, so seeing that's the case, I can plug in what I have for my value for L. It's 516. I have 2 times 516. If you prefer just to add them all up like this, nothing wrong with that at all either. You can use this or you can use this. You can just add all the sides separately, or you can use a shortcut formula if you remember how to use it. And you have 2 times 380 for the width. This would be 1032 plus, looks like that would be 760. Adding those together will give you 1792. And this is in terms of feet. That would be my final answer. 1792, 1,792 feet if I walked around the perimeter of this plot of land. And part B, suppose the length and width of the rectangle are doubled now. What is the effect on the perimeter? So if this is twice as big from here to here, 516 times 2, that's 1032. So this is my new length, my new L. I've got another L up here that's going to be the same length as that. And then down here, 380 times 2, that was 760. So 760 feet is my new W. And again, it's the same over here. So I can use my shortcut formula if I want, which I'm going to do. 2L plus 2W. And I know L is 1032, so I can plug that in. I know W is 760. Plug that in, work it out. This is 2064 plus, this looks like it'll be 1520. Adding those 2 values together gives me my final answer, 3,584. And that is in terms of feet. So that's my final perimeter, I should say, not exactly my final answer. This is very important to help me answer the question, what's the effect on the perimeter? So how much bigger is this compared to this? If you just divide that by 2, you get the perimeter of the old one, of the plot of land before it was doubled. So this shows us that the perimeter doubles when you double the side lengths. So you might say, well, that doesn't seem all that interesting. I feel like that was fairly obvious, intuitive, Mr. Wagner. Well, this is kind of leading us into something we'll learn more about later. Watch this. If I move this rectangle here, and I talk about area, so filling in the shape, what's the area on the inside? The area is actually what? 1, 2, 3, 4. Oh, look at that. It's actually quadrupled. So we'll learn a lot more about that later, but if you double the perimeter, or if you double the side lengths, the perimeter doubles as well, but the area actually gets multiplied by 4. Interesting. But moving on to a third example. Now we have Daphne. She's a pilot living in Alpine Lakes. Here's her town around there. Man, that is beautiful. She needs to drop off supplies to Bigfoot Junction and then to Castle Creek before returning home. Suppose these towns can be represented on a coordinate plane. Here's our coordinate plane, partitioned into miles with the points A at 6, -2. So 1, 2, 3, 4, 5, 6, and down 2. This is going to be point A at 6, -2. That's representing Alpine Lakes. B is at 1, 5, over 1, up 1, 2, 3, 4, 5. And I think it's important to note here that unless I tell you otherwise in the notes, you can assume that the grid lines will just be 1 unless I write that it stands for 2 or 3 or something like that. And then C is at -4, -7. So over 4 to the left and down 1, 2, 3, 4, 5, 6, 7. So all the way down here for Castle Creek. This is -4, -7. So we're going to find the total distance Daphne will fly on her trip around your answer to the nearest 1/10 of a mile. So she lives in Alpine Lakes. That means she's going to start there. So this is where her plane is. She's going to fly out of here to, use blue for this, to Bigfoot Junction first. So she goes there first, and then she flies to Castle Creek from Bigfoot Junction. And after that, she returns home. So we would take this path to do that. And from there, we should be able to find our answer. How far is this going to be? Well, it's going to be the perimeter of this triangle that we just drew. So it's this, whatever length that is, plus that, plus that. So we have a couple different ways we could do this. Since this is on a slant, I guess you could say, we can't just count the number of squares. It's not as simple as that. If it was just going straight up or straight to the left or right or down, yes, then it would be that easy. However, we're going to have to use either the distance formula 3 times, because we have to find 3 different lengths of segments, or Pythagorean theorem 3 times. If you want to use distance formula, go ahead. If you want to try to work it out, make sure you're using a pencil in case you make a mistake. But go ahead and do that if you prefer distance formula. I, however, am going to use Pythagorean theorem, and I'm going to get out another color, and I'm going to use some hidden lines for this. So I'm going to go with this and red. If you don't have a different color, at least do this part in hidden lines if you want to do the Pythagorean theorem method. So I've got a right triangle right there. That would let me figure out the length of AB. I've got another right triangle down here. This would let me figure out the length of AC. And finally, I've got a third right triangle right here. This would allow me to figure out the length of CB or BC. So I'm going to partition my workspace over here into 4 different parts. I'm going to have to do Pythagorean theorem 3 times, and then I'm going to have to add those values together. So let's do this like this. I think this is a good idea for you to do as well if you're taking notes here. So let's split this up into that. This is not another set of axes. This is just splitting my workspace up into different parts. So I know that these would be little right angles here, 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 and down here. But really, I don't need to know that that's a right angle. I just need to know that these 3 are right angles. And now I'm going to use Pythagorean theorem. If you, again, want to use distance formula, if you prefer the square root of the difference in the y's squared plus the difference in the x's squared, go ahead and do that. and see if you get the same thing. No problem with that. So I'm going to start with AB, start with the first leg of her journey. I know that leg squared plus leg squared equals hypotenuse squared. A squared plus B squared equals C squared. I need to know how long these legs are. So I'm going to get my red back out again. How long is it from here to here? I'm going from -2 as a y value up to 5 as a y value. That's a jump of 7. And then I'm going from 6 over to 1. That's a jump of 5 right there. So it's a 7 and 5. While I'm at it, I'll do the rest of these. So this is going from 1 with my x value for B over to -4. That's a difference of 5. This is going from 5 all the way down to -7. That's going to be a jump of 12 right there. This is -4 over to +6. That's 10 for that length. And then this one from -7 up to -2. That's another 5 right there. And so now I have all the information I need to use a Pythagorean theorem to figure out the lengths of each one of these hypotenuses, each one of these different parts of the journey. I'm not sure how you say hypotenuse plural, but hypotenuse here. You've got a squared plus b squared equals c squared. Leg squared plus leg squared equals hypotenuse squared. So I could say that that is 5 squared plus 7 squared equals AB squared. This would be 25. This would be 49. This is still AB squared. Add those together, you get 74. And then take the square root of both sides. The square root will cancel with this square. We're not talking about simplified radical form yet. I say yet because we may very well be doing that later in this course, but for right now it says we can round our answer, so I don't need to even think about doing something called simplified radical form yet. This is very important for us. I'm going to leave it as an exact answer for now, and then I'll round it off in the very end. That's always best. If you can leave stuff as exact answers until the very end, please do that. BC now, the second leg of her journey. So she went here first, now she's flying to Castle Creek from Bigfoot Junction. That's a 5 squared plus 12 squared equals BC squared setup. 5 squared is 25, 12 squared is 144, BC squared still BC squared. Add those together, you got 169. And if you take the square root of 169, you actually get a whole number. So this is something we call a Pythagorean triple. When you have 3 integer values, 3 whole number values for the side lengths of a right triangle. So 13 is BC. So square root of 74, and then 13 miles going this way. Back home now to Alpine Lakes. We've got 5 squared plus 10 squared would equal AC squared. You could say CA squared as well. 25 plus 100 would equal AC squared. This is 125 equals AC squared. Take the square root of both sides again. This one in simplified radical form, if you want to try to do that, or if you think you remember how to do that, you would actually have 5 times the square root of 5. That's what that one would be in simplified radical form. However, not getting into that in this lesson, I can leave it like this for now since I'm going to round it in the end. And so now the perimeter of this whole triangle, P is talking about the perimeter of triangle ABC. This would be these 3 values added together. So it's AB plus BC plus AC. I can replace those values in the letters and symbols with what they equal. So I have the square root of 74 plus a plain old 13 plus square root of 125. And if you put that into a calculator, notice I'm using an approximately equal to sign. It's not exactly this, but approximately this. The nearest tenth of a mile, this would be about 32.8 miles. Don't forget your units, since I did include those in the problem. 32.8 miles is how far she'll have to fly this plane. Watch out for Bigfoot. And a final example, example 4, says the length of a rectangle is 8 centimeters longer than its width. The perimeter this time is given to us. It's 42 centimeters. Determine the length and the width. So let's call this the length. Let's call this the width. And I know the length is equal to the width plus 8. If it's 8 centimeters longer, then it's width. So I can say L is the same thing as W plus 8. The same thing would apply at the bottom. L is W plus 8. So what do you have here? The perimeter, I'm told, is 42. So why don't I write that off to the side over here? The perimeter is 42 centimeters. That sounds pretty important to me. So if I add these four up, in other words, I get 42. So my perimeter is the same thing as it was before, length plus width plus length plus width. If you wanted to use the shortcut, 2L plus 2W, you could. But I'm replacing, and good time to color code once again here. I'm replacing the P, the perimeter value, with what it equals, with 42. That's why I wrote out the formula in general first, because it makes it easy to plug in the missing pieces, or plug in the pieces I know, and then solve for the missing pieces. L is the same thing as W plus 8, so I can replace L with W plus 8. And I have that written twice, so I've got another W plus 8 for this L. Putting that all together, combining like terms, how many W's do you see? I see 4 of them. How many integer numbers do you see if you add those together? 16. And we have 42 equals 4W plus 16. I'm rewriting it. What am I doing? I'm not sure. I need to do the next step. I need to subtract 16 from both sides. This would cancel. That leaves me with, on this side, 26 equals 4W. Dividing both sides by 4. 4's cancel, gets me W by itself. And W is representing my width. So this is one portion of my answer. So length and width. We're going to do the width here. This is going to be 6.5 or 6.5. It's not a nice whole number, but that's okay. And did they give us units? They sure did. Centimeters, so this would be centimeters. This is one part of 2 of my answer. Wow, that was a good straight line right there. I don't think I've ever drawn a straight line that good on this little tablet that I have here. So 6.5 equals W. That means that L is equal to, it's W plus 8. It's 6.5 then, plus 8. And that equals 14.5. This would be in terms of centimeters. We should check our answer if we can, which we can in this case. Yeah, that didn't go quite as well, but you get the point, still boxed in. So if I add 14.5 and 6.5 together, that would give me from here to here added together. So 14.5 plus 6.5, that'd be 21. And then I would have another 21 for that part and that part added together. The whole thing then would in fact equal what I started with, knowing the perimeter was 42. So did it check? It sure did. We're good to go. That's it. That's the final slide. As always, make sure you check these terms out and see if you got them all down now. If you don't, go back and review as needed. That's it for Chapter 1. We'll be moving on to Chapter 2 shortly. Make sure you study hard if you have a test that you're taking on this sort of material. If you're one of my students, yes, you are taking a test on this material. Make sure you know what to do and how to do these kinds of problems. Let me know if you have any questions. Have a great day, and I will see you later for Chapter 2.